Welcome to the Chess AI Visualizer demonstration. We've built our game environment this week on Flask and Socket.io application. This provides real-time communication between the web interface and the game engine using WebSockets. This architecture allows for instant move updates and smooth gameplay. Let's start the system and let's see how the engine game environment looks. Now that the system is running, let's explore the user interface. I'll start by clicking on human versus human mode for the first demonstration. On the left side, we have the interactive chessboard, the same graphics used on professional chess platforms. The board is fully responsive and supports both drag and drop and click to move instructions. Above and below the board, you will see player information panels. These display whose turn it is and a countdown timer. Each player starts with 10 minutes on their clock, and the timer is synchronized perfectly with the gameplay. It counts down in real time while a player thinks about their move. On the right side, the control panel provides the game controls. It has a button for a new game, undoing the last move, and resigning if needed. Below that is a toggle to highlight legal moves. When enabled, hovering over pieces show all possible destination with a blue highlight. When you untoggle it, it won't show any of the legal moves. The game statistics section tracks the mode, total moves played, whose turn it is, and the current game status. Move history displays all moves in algebraic notation as they are played. We use the standard format move number, then the move. The post-game analysis section will show detailed analysis once a game concludes. This will be added on later when we'll have available analysis for the engine later on. Now let's see the human versus AI mode, which showcases our system's ability to play as an intelligent opponent. For now, the AI only moves randomly, but later on, that will be powered by our game engine that we'll develop. So we can choose the color. I'll take white to start. Um, Notice as soon as the game starts, the AI will immediately respond with a move back. That was castling, which is also coded in. We've also added pawn promotion in this. So if my pawn goes all the way here, it will be able to promote itself. The rest of the feature remains the same. And as I said, the game once the game engine is ready, the AI will be powered with that engine. An important aspect of the system is data generation. Every game played, whether human versus human or human versus AI, is automatically recorded for training our model later on, or for reviewing where the games went wrong and to tweak the model later on. So, as you can see, this is the structure with which the game is stored. It's all the moves, and it shows the result, the move count, the entire time it took for the game to run, and the game ID and which mode it played in.
So, hello everybody. I'm Aditya and I'm here to talk about the pre-processing which we did for the final project. Um, Essentially, uh, we have uh, we we took over the compressed leeches databases from September 2025. Each file was decompressed 8 gigabits compressed and expanding over 40 gigabits when decompressed. That's way too much data to load into one memory. So our solution was streaming. So you can see the function stream from compressed. Stream from compressed use function uses z standard cat to decompress games on fly. Think of it like Netflix. We process one game at a time, never loading the entire file into the memory. Each game is read, processed, and immediately discarded. Then we add quality checks for the training dataset. We have had it four quality checks. First primary quality check was the ELO filter. Both players must be rated 1900 or higher. That's strong club player level. We added a time control quality check where only games with 10 minutes plus and no other bullet or blitz chaos games were present. Then we had a game length where between only 20 to 150 moves filter. Sorry, 15 to 200 move filter. Uh, to filter out early resignations. And then clean termination, wherein there were only normal endings, no disconnects or cheating. Then we encoded the board in, you can see, from board to tensor, which converts each chess position into a format where neural networks can understand. We create 12 channel tensors, 6 channels for white pieces, pawns, knights, bishops, rooks, queens, and kings, and 6 channels for the same black pieces. Each channel is an 8 by 8 where one piece present, 1 means piece present, and 0 means empty. Then we went to move encoding, which is the function move to index. The function converts moves into integers. There are 64 squares on a board, and so each from square times 64 plus 2 squares gives us a unique number from 0 to 4095. So move E2 to E4 becomes an index 804. Now results encoding. The result encoding get result value, which is here. Uh, we encoded the game outcomes into trainable labels. So white wins would mean +1, black wins would mean -1, and draws would be 0. But here's the trick. We flip the sign based on whose turn it is. So the network always learns from the current player's perspective. Now the main pipeline, which is the create dataset, has orchestrated the whole flowchart of multiple functions shown above. We stream millions of day games, apply our four filters, skip the first five moves of the game as we want only middle game positions. For each remaining positions, convert the board to tensor, encode the move, and record the results. 1000 games, we print progress. Once we hit our target, say 500,000 in our case, 500,000 positions, we stop and save. Lastly, we added our results into an NPZ file. The NPZ file is a compressed NumPy file containing three arrays, 500,000 vote positions as 12 cross 8 cross 8 tensors, 500,000 move indices, and 500,000 game results. We use float 16 precision to save space, cutting file size in half and without losing accuracy. Now moving on to the CNN architecture. This is a simple chestnut CNN architecture which we created. This was a bunch of input convolution layers, batch norm, and the hidden convolution layers with some policy heads and value heads. Uh, the current training for the CNN architecture is taking a lot of time, and hence this activity will be taken for the next week.